Can you hear me okay?
Yes, we hear you fine. And we see your presentation.
All right. Let me try to get it up on my screen. Well, fantastic. Like you've already introduced me, I am still Grace, and I'm delighted to be here. This is my first Icons, and I really enjoyed listening to all the talks today and seeing the wonderful work that you're all up to. I will briefly tell you a little bit about the National Science Foundation, which has been around since 1950. It was actually founded to promote the progress of science, to advance national health, prosperity, and welfare, and to secure the national defense and for other purposes. Primarily, NSF does very important research. It is vital because we support basic research, and Hal already gave you a great definition of basic research. So we support basic research and people to create knowledge that transforms the future. And this type of research is a primary driver for the US economy, and it enhances national security, and it advances knowledge to sustain global leadership. NSF is a rather large funding agency with an annual budget of about $8.3 billion based on fiscal 2020 spending. And like AFOSR, we spend a lot of our money, 93% of our budget, on research and education and related activities. We fund discovery, learning, and innovation research infrastructure to boost US leadership in all aspects of science. And we're different from mission agencies in that we don't pick one topic, such as health or energy. We fund all topics. In FY20, NSF received about 48,000 proposals. Out of those, 12,000 were funded, supporting 2,000 institutions and over 386,000 individuals. We also invested in 1.2 billion in STEM education and gave 200 million to small businesses. And a small fact is we're very proud of our at least 248 Nobel Prize winners last I checked. This is an org chart for the NSF. We're composed of lots of rotators, so I thought it was easier to show you a manila org chart and explain that the NSF is an independent federal agency. We don't fall under any cabinet department. NSF's activities are guided by the 25-member National Science Board, which also serves as a policy advisory body to the President and Congress. Our director answers to the National Science Board, and there are 7 directorates at the NSF. And I am part of the engineering directorate. And what I will do in this talk today is tell you about what the Directorate for Engineering is doing in the area of neuromorphic engineering and discuss an exciting opportunity, brain-inspired dynamics for engineering energy efficient circuits and AI, which we'll call BRAID for short, as well as tell you some existing neuromorphic engineering opportunities in the engineering directorate. So within the engineering directorate, there is a division that's responsible for emerging frontiers and multidisciplinary activities. They're called EFMA. And their primary purpose is to provide critical strategic support for fundamental discovery at the frontiers of engineering research and education. Now, EFMA does this through its Emerging Frontiers and Research Innovation Program, and that's what we call the F3. The F3 investments represent transformative opportunities, potentially leading to new areas for fundamental or applied research, new industry or capabilities that result in leadership position for the United States, or significant progress on a recognized national need or grand challenge. The way the F3 program identifies opportunities is that it seeks continual input from the engineering community through calls for new F3 topics. And these days, the F3 topics are competed once every 2 years. Ideas can be generated internally by program directors or by people like yourself from the external community. This past year, over 300 entries were submitted. And the way the NSF de-anonymizes all the entries, and a very rigorous process is implemented to evaluate the quality of the ideas. And these ideas are evaluated based on 5 criteria: whether the idea holds potential for transformative outcome, addresses a national need or grand challenge, involves multiple or interdisciplinary research, includes a community who is poised to respond, and offers a clear leadership role for engineering. It's a really rigorous process. If this sounds like something you're interested in, keep an eye out for the F recall in a year and a half from now. It involves a white paper and a presentation to a panel of external experts from academia, industry, and government. And out of all these submissions globally, only 2 topics are chosen. Historically, these topics are about $30 million each. And they run for 2 cycles. In this case, it's going to be for fiscal year 22 and 23. And each award is about $2 million with a 4-year period of performance. Based on historical trends, 7 to 8, not 78, 7 to 8 projects are selected per cycle. And over the course of the 2 cycles, 15 or so 2 million projects are selected. So this year, I'm delighted to announce that one of the FY22 EFRI topic was the braid topic that was developed by myself and inputs from others in the neuromorphic engineering community, including folks that are in this audience, and with inputs from other National Science Foundation program directors and inputs from other panelists in this session. So this is really, really exciting because the last time there was a call like this in the history of the EFRI program was 14 years ago, back in 2008. So I think this is a very exciting time that there's a lot of energy for neuromorphic engineering in the immediate future. So I want to give you a little bit of background about this formation of the EFRI topic. There were 2 primary drivers behind BRAID. The first driver was out of concern for sustainability. With deep learning algorithms on a trajectory of needing more and more data and compute cycles, I'm sure you're all aware of OpenAI's GPT-3 that uses 175 billion parameters, and one of its 5 training data set was the entire corpus of the internet the last I checked. So clearly this is not a sustainable trend. And as Hal and others already mentioned, the brain, on the other hand, is an existence proof for data and power efficient learning. The biological brain is able to learn continually without catastrophic forgetting. It can learn from low sample examples. It can learn causally and over an entire lifetime of an animal. No AI or neuromorphic chip can accomplish what the brain has evolved to do. And the brain does so at a fraction of the power budget compared to CMOS technology with equivalent number of transistors for synapses. So the brain uses a diversity of cell types, complex temporal codes, and self-activation mechanisms to learn at multiple spatial temporal scales. Now, could temporal dynamics across tens of spatial temporal scales be critical for biological learning? So that was one of the main driver for the BRAID topic. And the second main driver was inspired by the significant advances in neuroscience and neurotechnologies over the last decade by the global brain initiatives in the United States, the UK, and in China. Thanks to these brain initiatives, our understanding of the brain has ripened to the point of being able to inform algorithm and hardware design. The BRAIN initiative has identified new cell types in computation with no analog in current AI methods or neuromorphic engineering. Now, Hal mentioned one of those cell types in his talk. The technologies that's been created by the BRAIN initiatives allow us to measure simultaneously from thousands, if not millions, of neurons while animals are conducting causal tasks, so that we can see how memories are created and how decisions are made. These physiological signals can be converted to algorithms, code, and new architecture to advance AI in hardware and software. Now, unlike the BRAIN initiative, or at least the US BRAIN initiative, which continues to develop theory and technologies for understanding the brain, the BRAID topic will develop theories and technologies for advancing engineered learning systems. So BRAID is about leveraging neuroscience in the service of engineering. And as you can see on this slide, the BRAID EFRI topic will support fundamental research towards understanding applying dynamical neuroscience to leverage the unique features of biological learning and decision-making for engineered learning systems. And these features, clearly include energy, data, flexibility of the brain. And we hope to achieve transformative engineered learning systems that can incorporate breakthroughs in neuroscience. We hope to achieve generalizable, energy efficient AI systems that could operate with human level intelligence. And we hope to democratize and accelerate the deployment of ethical brain-based AI and edge sensor systems. So this next slide, if I can get it to advance, that's curious, is a cut and paste of the press release that was issued back in April of this year at the Nsf Engineering Advisory Committee meeting. It took place in April, and you're welcome to take a screen capture of it. I've already, mentioned most of what's on this slide. BRAID will build on recent advances in neuroscience to stimulate and transform innovation in AI and engineered learning systems. One of BRAID's key goals is to catalyze a convergent research community comprising teams of engineers and neuroscientists and other disciplines to accelerate the field of brain-inspired engineering systems. The BRAID topic will encompass 3 focus areas. Theoretical neuroscience is one of them. Brain-informed circuit design is the second focus area, and algorithmic learning will be the third focus area. And the hope is that these areas will reciprocally, cooperatively, and ethically advance foundational knowledge for future advances in engineered learning system. Now, the solicitation has not been released. So if this interests you, you can see my email. You can send me an email with the title BRAID mailing list, and I'll make sure you're added to the mailing list. What typically happens is a solicitation will be released sometime this year, and after it's released, there will be some kind of an information webinar that was set up, and then a letter of intent would be due, followed by a preliminary proposal, and then the successful preliminary proposal will be invited to submit a full proposal. So I don't know, how am I doing for time?
You've got about a minute before questions.
Okay, so with that, I want to just say, sorry, I can't seem to advance my slide. That there are other programs in the Engineering Directorate that also support neuromorphic engineering. And if you go to this landing site, www.nsf.gov/rehab, you'll be able to click on to a variety of different programs, and 2 of them highlighted in red here also support neuromorphic engineering. And these are solicitations that are open. There are no due dates. And if you're interested in submitting something to either the DARE program or the M3X program, the best thing is to contact myself if you're interested in disability and rehabilitation engineering, or to contact Bob Scheit. His email's at the middle of the slide, the bottom of the slide. And send us a white paper, a 1-page white paper. If you email us, we could send you a template for that 1-page white paper, because it's much better to write a 1-pager before writing a 15-page white paper. So save yourself some time if you're interested. And the last thing I'll mention is that Dr. Ken Wang, who will speak after me today, we'll talk about 2 other programs at the NSF that also support neuromorphic engineering. And that's presented on this slide here. So with that, I think I have made my time.
Thank you, Grace. That was excellent. We really appreciate the input, and it's exciting what you're with the BRAID program. Congratulations on getting that through. I know that took a lot of work, but that sounds like a very exciting program. Are there any questions? Well, I'll ask a question. So one of the challenges in the neuromorphic area and sort of how reference this is how to get people to sort of interact, how to get the electrical engineers and the computer scientists and the neuroscientists and the material scientists, how to get them to meaningfully interact. At times it seems like you could spend a couple of years just learning each other's language and all that. How do you see doing that in your program? Well,
that's a great question, and that's something I I think about a lot, trying to catalyze the interaction between the different fields of engineering and the neuroscientists. You know, the way the NSF works is we will have this webinar, which will introduce respective program directors will be able to communicate at that webinar to engage their respective communities. And I think that is one small step in the right direction. But clearly, I think having a mixer where we invite different people from different disciplines to come together and really engage and talk about, you know, get on each other's page would be a fantastic thing to do to help catalyze that interaction, so that by the time they're writing a proposal, they're already speaking each other's languages. Now, I will say that because we've had ongoing interdisciplinary programs that Ken Wang will discuss hopefully in 15 or so minutes, there is a community of people that are already thinking across multiple disciplines. And I think it's programs like that that preceded BRAID that will really help us realize this hope of getting very effective interdisciplinary communication right from the get-go. But I think there's more work that needs to be done to bring in the material engineers and the physicists and the non-traditional, non-neuromorphs, if you will.
Well, I appreciate that. And it's one of the things that we've tried to do with the Icons conference, and it's you know, it was a little more interesting when we could be face to face and you can have a cup of coffee with somebody and sort of go, well, you know, I don't understand what you're talking about. What is that? You know, and then you kind of go, oh yeah, I see it. It's a little more challenging on the virtual end, but anyway, I applaud your efforts, and it sounds like you've got a great program, and I imagine you'll get a number of folks connecting with you. Anyway, well, thank you very much, Grace. Excellent talk. We really appreciate it.
I think I see a hand. Is that a fake hand?
Oh, I'm sorry. Yes. Yeah, Miriam.
Thank you. Yes. Thank you so much to Grace and also Hal for great presentation. So I have a question. So I'm a joining faculty at George Mason University starting this fall. My question is that, do you have any specific call for I don't know, assistant professors? Because a lot of time, one of my stresses is that a lot of time these calls are more tuned towards senior PIs. They are well known in the field. So is there any specific call you recommend new faculty to submit proposal?
I think that's a perception. I do not believe that any NSF calls is tuned to senior faculty. I think we really like to engage with new time PIs. In fact, it's you know, yeah, and there are early career opportunities. So the career proposals are actually, they were due yesterday, but because of an IT glitch, they're now due tomorrow. So but yes, there are solicitations geared to early career PIs like yourself. Ken, would you like to add to that? Since
yeah, it also depends on which field you're in. So in the Science Directorate, there's also something that we call the Research Initiation Awards, which are sort of like even earlier stage than career. But you know, but I would also say that in our regular programs, you know, being able to launch new careers and supporting young PIs is definitely something that you know, both panelists and program officers like to do.
Thank you. Thanks.
Right.
Can I add also
Please.
all three services in the DoD, so Army, Navy, and Air Force, all have the Young Investigator Program, which is for people who have a tenure track faculty position or permanent position and are within 7 years of receiving their PhD.
Awesome. Thank you.
But there's no limitations either. I've given a traditional grant to someone who was just starting their new faculty position, and that was their first grant.
Thank you.
Oh, wonderful. Great question, Miriam. Anyway, thank you, Grace. We really appreciate it. Wonderful talk. Thank you again.
Thank you.
All right. Now we'll move on to Robinson. So Dr. Pino is a computer scientist and program manager in the Advanced Scientific Computing Research Program, ASCR, at the Department of Energy Office of Science. He focuses on revolutionary basic research and development efforts in high-performance computing and applications that will enable our continued leadership through exascale and beyond computing. And I just lost my, there we are. Dr. Pino has expertise with technology development, program management, government, industry, and academia. His research and development focuses on intelligent, autonomous, and cognitive applications towards network, host, and mobile security solutions. Robinson has a PhD and master's degree in electrical engineering from Rensselaer Polytechnic Institute. On a personal note, Robinson was the founder of this conference, and he's a great friend, and we're looking forward to hearing from you, Robinson.
Well, thank you all for being here, and I'm looking forward to the presentation. Can you guys hear me well?
Yes, and we see your slides.
Okay, great. So I'm in the DOE Office of Science and the Office of Advanced Scientific Computing Research. And I'm gonna talk about DOE activities in neuromorphic computing. And like Tom mentioned, we've been working on this for, I would say, for over 5 years now. And we've come a long way, and we're here today. And I'm gonna talk to you to some activities that we've done and some that may be coming in the future. So for those of you that may not have heard about the DOE, we have multiple mission areas, obviously in energy, power grid, oil and gas, solar cells, nuclear security and safety, and the area that I'm in is in science and innovation. In the DOE Office of Science, we're responsible for 10 of the 17 DOE national laboratories. Here's a snapshot of all the national laboratories that we steward. And one of the things that underlines our mission in science is the need for advanced technologies, whether it is from hardware, from sensors, from software, to being applied to large-scale scientific user facilities. We use a lot of those technologies. In DOE, we support thousands of researchers annually, over 30,000, and all of them, a lot of the research that we do is geared towards our large-scale scientific user facilities. However, as we look into the future, a lot of this research that we support, well, some of the research that we support, like in neuromorphic computing, tries to pave the way for the future. And a lot of that work obviously is in partnership with other federal agencies. My office in particular is quite well known for sponsoring and supporting the supercomputers, the leadership class supercomputers in the US. And we are getting close to having exascale supercomputers to begin to be deployed in our national laboratories. And that will open a new chapter in computing. But even so, we're moving towards the future, and we have these very large-scale computing systems. There is still a lot of need for intelligence, for adaptability, and for knowing more about what biology is and what biology has to offer, such as from neuroscience, and even simple biology, DNA, the brain. And it is it's becoming obvious that we need all of these technologies to be able to ensure that we can continue to progress as a society, to be able to solve the problems that we have, and to be able to continue moving forward. So here's a snapshot of the early activities that we perform. Many of you have contributed to all of these activities. To start the DOE area of neuromorphic computing, which we started about 5 to 6 years ago, and where last year we had our first funding opportunity announcement in neuromorphic computing, and hopefully there will be more in the future. In addition to looking at neuromorphic computing from a software and algorithmic point of view, it became very clear that in order to make advances in future computing, we need to invest in hardware. And the hardware that we need to invest may need to be different from the hardware that we consider today to be the state of the art. So about 3 years ago, we did a workshop on microelectronics, and this year we launched the first funding opportunity announcement for our national laboratories in the area of microelectronics. And I hope that hopefully in the August timeframe, we can make announcements in this area. An area where not only computing for high performance computing needs are explored, but also neuromorphic computing, embedded computing, and advanced wireless sensors that are needed to continue global leadership. Also last year, and I know Ken is going to talk more about it, DOE joined the Collaborative Research in Computational Neuroscience, which is a collaboration that NSF has led for many years. That is international. Several countries are part of this collaboration. And this year, DOE, for the first time, will be making awards based on this collaboration, which is very exciting because it brings many aspects of this highly multidisciplinary and interdisciplinary area of research. Another area that we began investing in DOE is advanced wireless. We've heard about 5G and all the things that 5G could offer to the business world, to the personal world. But one of the questions that we have had is how could advanced wireless could benefit our mission in the scientific domains. And so this year we also announced the first funding opportunity announcements for our national laboratories. And we hope that in the future, we'll have more opportunities for 5G and microelectronics and neuromorphic computing that are open to academia and industry. Now, I've talked kind of a wide range of areas that we're investing, and they might sound like they're kind of all over the place, but they're actually connected. So today, when we talk about high performance computing, data centers, cloud computing, we all somehow we use it. We all use the internet, and maybe in our homes, in our personal devices, we have a lot of edge devices. And that picture can also be represented for our scientific needs in DOE, where we have a lot of facilities and instrumentation that could put that generates a lot of data. It continues to increase the amount of data it generates per year. That data needs to be analyzed. The data needs to be moved. Network connectivity can be limited from a physical standpoint. So wireless could offer an opportunity to connect a lot of the devices that we need the edge computing technology that might need to be developed to extract and analyze that data, and to move the data around so that we can use it, so that it can be analyzed. So at the foundational element, we see that microelectronics, as we move forward, will create opportunities for new devices beyond the state-of-the-art and integrated or mixed with the state-of-the-art sensors and systems on chips that can accelerate computing in general, whether it is digital, neuromorphic, or quantum. Before I end, I wanted to invite the audience to participate in a workshop that one of our applied offices, the Office of Energy Efficiency and Renewable Energy, the Advanced Manufacturing Office, is conducting a workshop in August with an emphasis on analog neuromorphic computing. And this is the website, and I'm also going to put the website link on the chat so that you can participate. So this is a workshop by one of our applied offices, and hopefully you'll take the time to contribute to this workshop, because not only from a basic research point of view, we do appreciate the input that you provide to our reports, but from an applied point of view, our sister office in the Advanced Manufacturing Office could benefit from your input, and hopefully it would lead to funding opportunities in this area. With that, I want to thank you all for your time, and I wonder if anybody has any questions. Thank you.
Thank you, Robinson. Katie.
Hey, Robinson, thanks for the presentation, and thanks to Hal and Grace as well. I'm excited to hear from Ken. So I'm a little bit jumping ahead on this because I think Ken's going to talk about it, but the CRC&S is really exciting to see different funding organizations coming together, DOE, NSF, and then as well as the international organizations, NIH, all coming in to sort of coalesce around a common goal. Do you see other opportunities for the diverse funding agencies, both domestically and internationally, to come together to coordinate efforts in neuromorphic?
I would hope so, and I think that as the need for new types of emerging computing becomes more clear, as results from this collaboration and from individual research efforts give fruit, I think, well, I'm going to make a prediction that it might be required. And one of the reasons is because of the level of multiple fields that need to be involved. And one of the reasons why we joined the collaboration is because to get access to the neuroscience components of the research that are outside of our mission space, but other agencies are very well versed in it. So I think we all benefit from these types of collaborations, and I do hope that they will grow and may grow in other areas as well.
Thank you.
Any other questions? Well, thank you, Robinson. I really appreciate your perspective and input, and thank you for enabling us to get this panel together. Okay. All right, our final speaker is Dr. Ken Wang. He is a program officer in the NSF Division for Information and Intelligent Systems, where he manages the computational neuroscience and other activities at the interface of brain research and computing. He did his PhD in neuroscience at the University of Washington and a postdoc at the University of Minnesota. He has worked for the US Senate for the Office of Science and Technology Policy before coming to NSF. And he is the proud owner of a pin given to him by the US government for 20 years of service at NSF. Thank you for your service, Ken. We really appreciate it. And we're looking forward to hearing your talk.
Great, thank you very much. All right. Are my slides looking okay? Okay.
Yes, yes.
Okay, great. Well, I'll follow up where Grace left off and where my other colleagues on the panel left off. I will say a little bit about some of the interdisciplinary programs that are relevant to neuromorphic engineering at NSF, some of the relevant programs in our NSF core programs, and then try to give a little bit of a perspective on navigating the various opportunities at NSF as well. To start with, most of you have probably had the experience of going to the NSF website at some point, and you may have run into the question of, how do I know which of these hundreds of funding opportunities is right for me? Who do I talk to find out? And really, depending on the kind of work that you're doing, the website can be more or less helpful. But you can think of it as a tool, an initial tool to help you get started, especially to get you connected to an appropriate program officer to talk to about your project ideas. As Grace mentioned already, NSF is organized according to traditional academic disciplines. We have a hierarchy of directorates and divisions, and what we call our disciplinary core programs sit within those directorates and divisions, and they tend to be pretty stable over time. So for certain disciplinary communities, you can pretty much find out where your colleagues have submitted, and if your proposal is relevant to roughly the same disciplinary journals and conferences, you can pretty much follow suit and submit to the same program. This disciplinary structure is also important to know because NSF program officers are also assigned to disciplinary organizations. So if you work your way through our divisions and programs and find a reasonably close fit, that's a good way to connect to an actual human being who will be able to give you advice, even if they're not necessarily spot on to your exact research topic. Now, for people who are working across disciplines, it's a little more complicated. We have other programs that we have that are called cross-cutting, just in the sense they cut across different parts of the NSF organization. And these address particular intellectual opportunities that cut across traditional disciplines. They get managed by teams of program officers working across different NSF organizations, and oftentimes they may also have special review criteria and tend to change more over time. So with that as background, I want to give just a quick run through of the NSF opportunities beyond those already mentioned that I think are at least worth the neuromorphic community to be familiar with. The CRCNS program has already been mentioned. And so for those of you who are working somewhere in the greater metropolitan area of computational neuroscience, this is a very inclusively defined program looking at a wide range of topics at the intersection of computation and neuroscience. It is a cross-cutting and interagency program. It involves 5 different directorates of NSF. We are very glad to have DOE's Office of Science on board as of this year. We have 9 NIH institutes and centers, and then we have several international partners as well. Now, there's a really strong emphasis here on collaboration and interdisciplinary approaches. And the point is that we want to bring people together to make significant advances on problems that are hard or too hard for any one of us to be able to solve ourselves. And so this is, in a way, a mechanism to support an interdisciplinary dialogue. Not only is the neurobiology providing certain models and existence proofs that we can think about from an engineering and computing side, but it's really the engineering and computing that are also bringing to neuroscience ways to think theoretically about the functions of these systems, about why is it that this particular biological detail is important for solving a particular problem, and so forth. So one interesting thing about this program was when we started this program almost 20 years ago, the kind of dialogue that we had was very different from what we have now, and it wasn't really known at that time sort of how deep and interesting and continuing this dialogue has become in terms of the necessity of working together to really understand the functionality of brains and what that can tell us about computing and engineered systems as well. This program, considers research proposals. Most of the projects that come in are research proposals. It also includes proposals for sharing of data and other resources, which is another way that we get the community to collaborate together and to have some common ground for understanding systems and understanding analysis of these systems, based on common data sets and so forth. As I mentioned, also, we have several international partners from Germany, France, Israel, Japan, and Spain. And in this program, we have arrangements made such that you can have a joint project that involves the US and other countries, and the other countries will pick up the parts of the funding of the parts in the other countries, and the US agencies will pick up the US side of it. So it's another form of international collaboration, which I think may be quite relevant to many of the researchers in this community. Another program that we have, which is an NSF program, is called Integrative Strategies for Understanding Neural and Cognitive Systems. And in a way, you can think of this as being a program to generate some different kinds of dialogues between neuroscience and other disciplines, going beyond computational neuroscience and into other interactions between neuroscience, engineering, behavioral sciences, education, and so forth. So this program is built around 4 different focus areas: neuroengineering and brain-inspired concepts and designs, individuality and variation, data-intensive cognitive science and neuroscience, and cognitive and neural processes in realistic and complex environments. And we think of these 4 focus areas kind of as you might think of them as axes where people coming from different perspectives are trying to push the envelope in each of these different directions. And some of that pushing of the envelope is bringing people together from different disciplinary perspectives. Now, one of the aspects of this kind of interdisciplinary collaboration, it does involve a lot of learning of new languages, and it involves a lot of inherent risk. One of the things that we're looking for in these proposals specifically is we're looking really only for high risk, high payoff kinds of approaches. There are plenty of opportunities in other NSF programs for doing science that is sort of along more well-established tracks already. And this opportunity is really there to create some new tracks where people are coming together with quite different ideas and bringing them together to some new synthesis. So we have 2 different types of projects in this program. There are what we call the NCS Foundations proposals, which are collaborative proposals, roughly in the $1 million range. The next deadline for that is next February. And then we have a larger scale Frontiers mechanism, which brings multiple threads together. So these could be, $2 to $4 million, typically a larger team. This is something that we're competing biennially. So the next deadline for that will be a letter of intent in December of 2022 and a full proposal in 2023. For those of you who are in the artificial intelligence arena, NSF has made major investments in this area. Most notably, recently we launched the AI Research Institutes program, which is looking for large-scale centers. They're really, on the scale of engineering research centers or NSF science and technology centers, except that they're all bringing together different perspectives in artificial intelligence. And the idea of these centers is to do some combination of foundational AI research and use-inspired AI research. And the Research Institute's competitions are built around themes which are announced and updated each year. So this diagram here just shows you what the themes were for the 2021 competition. And you can look forward to seeing a new announcement of themes when the next solicitation comes out, probably late summer or early fall. Some additional opportunities in the SCI Directorate, just programmatically, we have the Software and Hardware Foundations core program in the Division of Computing and Communications Foundations. We get a fair bit of neuromorphic work there. This is interested in foundational research in both software and hardware, and including, getting software that works with hardware and vice versa. The Foundations of Emerging Technologies program includes biocomputing, neuromorphic computing, quantum, and Pinaki Mazumdar is our program officer there, who works on the neuromorphic part of that portfolio. In my division, the Division of Information and Intelligence Systems, the Robust Intelligence program includes computational neuroscience, artificial intelligence, machine learning, natural language processing, computer vision. It's sort of an umbrella program of all of these related areas. And we get disciplinary proposals sort of within these sub areas. We also get a lot of work now that cuts across these traditional areas. And then I also wanted to mention human-centered computing, which is also in our division and includes a lot of work on brain-computer interfaces, among other human-centered computing topics. Within our SCI's core programs, I also just wanted to mention that we are increasingly having opportunities for international co-funding for binational projects involving other countries. So currently we have arrangements with Israel, France, Finland, and South Korea. And if you search for NSF SCI's Dear Colleague letters, you'll come to a page that has all of the specifics for these international co-funding opportunities, and will be updated, if new arrangements like these come on board. Again, it does reflect our sense that a lot of this really is global enterprise, and we want to encourage our PIs to collaborate as much as possible. And then finally, as Grace mentioned, if you have questions, contact us, ask your program officer, identify an appropriate program officer, develop a one-pager, request a meeting. Talking to you about your project ideas is the most fun aspect of our job by far. And so we love to hear from you. We love to, get your ideas and, just give you all the advice we can about, how to prepare that to be a competitive NSF proposal and what venues would be most receptive to it. And then finally, our program officer staff, many of them come from rotator positions. They coming here for a few years from academic positions. So if you're interested at all at looking into this, either now or some future point in your career, take a look at our rotators website, and you can find more information about what that opportunity is like. And thank you very much.
Great. Well, thank you very much, Ken. That was excellent. We really appreciate your insight and thoughts on this. So, are there any questions? So, I have a question along the, you talked about the cognitive approach and natural language and sort of it gets a bit to the, sort of general AI. So how far away, how much of a pipe dream is general AI right now? I mean, do you think that's something that is achievable in 5 or 10 years?
It's a great question. And, I think one of the reasons that it's a difficult question is that the goalposts change, right? We solve certain problems that we thought were like, incredible challenges for their time. And then, and then once the problem is solved, it really is like that. I'm blanking on the classic the classic AI paper. Once the problem is solved, then we think somehow that it was no big deal. But in terms of having systems that are good enough to work reliably as as teammates with other people. Certainly I think that is something on the horizon. And then kind of where we go after that, I'm not sure.
Well, yeah, I think of facial recognition and language translation as being these unsolvable human only kind of problems, and except now it's like, oh yeah, so big deal. But anyway, it's a very interesting ideas. Are there any other questions for Ken?
Yes, funding opportunities for graduate students. Maybe I'll say something about really funding opportunities for graduate students and postdocs, because that those questions often come up together. GRFP is our principal funding opportunity where the student itself is the one who has won the award, right? And that means that the student can take the award someplace else, and the student really has power over how that award is used. The other main piece of graduate training is the NRTs, the National Science Foundation Research Traineeships. These are done at the institution level. They're done at the at the level of developing cutting-edge interdisciplinary training programs for graduate students. Now, at the postdoc level, training opportunities are really, in a way, they're more sparse at NSF than they are at some other agencies. We don't have anything that's sort of equivalent to what they have at NIH, for example, where they have something that that postdocs can apply for themselves. At NSF, the postdoc opportunities, they change a lot. If you go to the NSF website, you'll see a section for postdoc opportunities, and they tend to be for fairly special purposes and to change from year to year. Those are the opportunities where the postdoc, him or herself, is the applicant. But the other place where we see postdocs and graduate students involved is just through the regular research grants. So through the process of working with your mentor, typically on writing proposals, that they become key players in regular NSF research projects. That's where most of our funding ends up going, is to to trainee support. Obviously, some of it goes to faculty salary as well, but more of it goes to training support. And then for advanced postdocs, depending on what the rules are at your institution, oftentimes advanced postdocs are allowed to apply as PIs themselves. So that's another way that that trainees can get involved in NSF funding.
Great. Katie.
So I guess this is actually a question for all of you. So is there a key capability, like a large scale capability that you think maybe the US is missing that we need to make large leaps forward in neuromorphic computing? For example, like experimental fabrication facilities or something like that. Is there anything that sort of you think is hindering the progress? And is there a sort of a path forward to enable that?
Well, I'll speak a little bit outside of my expertise here, but maybe in an area where others can fill in. And, you know, one of the things that's really difficult in terms of large scale is that it's really hard to make chips. And I believe that there are, you know, some facilities that have been developed through other funders, not us, to make that more accessible to the experimental world.
I think there's also some effort on the the neural connectome to establish, you know, larger facilities to do large scale experiments for that as well. Yeah, I was just curious to see what the path is to realize some of those, you know, large scale facilities that might not be realized today.
You know, one thing that could be of interest, NSF has a competition for what we call mid-scale research infrastructure. Mid-scale, it doesn't really mean mid in the conventional sense. It just means that you're not asking for a whole telescope. And this has actually been one of the, you know, the so-called 10 big ideas that was launched by our previous NSF director. And the idea was that we really do have needs for, you know, research infrastructure in the, you know, tens of millions of dollars range, and not really any way, any easy way, at least prior to the mid-scale program, to fund it. Now, one of the things that's happened though is we really have not gotten a lot of applications in that space from, you know, in that program from, you know, from people who are in the neuroscience space. And so I'm not sure if that is because the community is, you know, is not quite ready to go there, or if it's because, you know, we need to actually do more active organizing on our part in terms of bringing together workshops and looking at that issue. So I don't know the answer to that question. I feel like in that respect, we may even have some opportunities that are somewhat undersubscribed.
Thank you.
Miriam.
Thank you. I also have a quick question. So how can we join review panels? Because I think I found that really helpful for us to learn how to write good proposals, and the experience is really helpful. So could you please comment on that?
At NSF, we are always happy to get people who want to volunteer for reviews. The best thing is to contact your program officer, send a CV, you know, just a short email saying I'm interested in, you know, XYZ topics, and we'll do our best to plug you in. And indeed, you know, there is no substitute for being on the other side to just, you know, get a sense of how proposals get evaluated, and also how to present your own ideas more effectively.
Thank you.
All right, everybody, last shot. You've got 4 program managers ready to answer your questions. All right, well, it's late in the day on day 1. I really, really appreciate everybody's the outstanding invited talks. This was a great perspective to see sort of the other side and get a sense of where the where things are headed in the neuromorphic area and the neuroscience area and the AI area. It was phenomenal to hear, and I really appreciate all of your time and energy and efforts to come and be with us. You are always welcome at Icons, and we hope you come back in the future. But thank you very much. Great job, everybody. All right, Katie, do you want to close this out?
Yes, so we will resume tomorrow at 10 a.m. Eastern time. We have a great keynote by Julie Grelier on materials and devices in neuromorphic computing tomorrow. I'm very excited to hear from Julie. I hope you all will join us for that. Tomorrow is more hardware oriented. We're going to have some algorithms for hardware talks in the mornings, as well as some lightning talks for hardware in the afternoon. And then tomorrow afternoon is our poster session. So please join us to interact. We're going to have breakout rooms for every one of our poster presenters. You'll have the chance to interact with them in a smaller setting. I also want to point out for all of the students, check out the chat, because they were all dropping links in the chat for different opportunities for graduate students. So I just want to call that out to you. Grab that before you sign off today. So thank you very much for attending today. We'll kick back off at 10 a.m. Eastern tomorrow morning.